Right, I'm going to talk about Christchurch groundwater. And I was looking at this title slide before and thinking, is that title a bit dull? But then I thought, I am a groundwater scientist, and Christchurch groundwater, it doesn't get more exciting than that, so the title stays. What I want to talk about today is how the groundwater system works and what Christchurch groundwater is. And it is actually quite exciting. If you think about it, we got a city of 400,000 people sitting right on top of this groundwater system that provides us all with drinking water that doesn't need chlorine to treat it. We turn on the tap, we get beautiful drinking water. And on top of that, the groundwater feeds the rivers that flow through the city, the Avon, the Heathcote, the Styx, the rivers that really add quite a lot of beauty to the city. It's not adding quite as much water recently as it has sometimes, and I'll talk about that a bit later on. But what I want to talk about first, before I get to the stream flows, is just an overview of the groundwater system, how it works. What is groundwater? Where does it come from? Where does it go? And after that, get into a little bit about what risks are there to the groundwater system and what do we need to watch out for. And then at the end, come to that question of the flows and the streams. Now, to start with, I'm going to step back and look at the situation of Christchurch sitting on the Canterbury Plains. The Canterbury Plains is basically a big pile of gravel, several hundred meters thick. If you step way back, we've got tectonic plates crashing together, lifting up the Southern Alps. As the Southern Alps rise, the elements knock them back down. Rain, ice, wind, turn them to rubble. And braided rivers flowing out of those mountains carry that rubble out of the mountains and deposit it on the Canterbury Plains. And that's been going on for a couple million years. All those gravels are filled with water. It's a bit like, picture you've got a glass in your hand, a clear glass that you can see into, and you fill that glass with sand. Now, you're holding a glass full of sand, you pour some water into that glass. What happens? The water, you can actually watch it because you can see through the glass, you can watch it percolate down to the bottom of the glass, and it starts filling up the glass, and you can watch that water level in the glass rise. That's essentially what groundwater is. What you've got in your hand is a little groundwater system. If you stop filling the glass before that water level gets quite to the top of the sand, you've got something very much like the Canterbury Plains. That water level, the surface of the water, is the water table. You can't see it from the top, but you know it's there, and you can see it when you look in the side. And if you want to, you can make a little well. You could take a straw, stick it into the sand, and as long as you stuck the end of the straw down below that water table, you could suck on it and you'd get water out. Now, the Canterbury Plains is a bit more complicated than that, obviously. It's a lot bigger than your glass of water in your hand. The gravels that lie beneath the plains are a lot more complicated than that nice, clean sand you've got in your glass. They're deposited by braided rivers, which, if you've ever stood in the bed of a braided river, you'll see that there's lots of crisscrossing channels and lots of variety between some channels of nice clean gravel and other channels that are much sandier and some piles of silt here and there. But overall, over the course of the plains, you've basically got this big pile of complex gravel. The other difference between this little aquifer in your hand and what we've got on the Canterbury Plains is that in the glass of water, the water's not going anywhere. It's just sitting there, and that water table is flat. Beneath the Canterbury Plains, the groundwater is flowing. It's flowing basically from the mountains down the plain to the ocean. And because it's flowing, the water table isn't flat. The water table slopes basically parallel to the direction the groundwater is flowing. In fact, that's how we find out what direction the groundwater is flowing. We can measure the level of that water table across the plains, and we can do a survey and contour it and make a map of where that water table is. And that tells us what direction the groundwater is flowing. And I said that basically the groundwater flows from the mountains to the sea, but there's a little bit of variation. These arrows basically show what we found to be the groundwater flow directions. And you can see, certainly in the central part of the plains, it's basically flowing straight to the sea. But if you look in the north, that arrow north of the Waimakariri River, that's bending a bit to the north. The Waimakariri River is actually deflecting the flow of the groundwater a bit to the north. If you look on the south side of the Waimakariri, you'll see an arrow leading from the river underneath the city of Christchurch. A bit farther to the south, the arrow curves to the south. The groundwater is basically flowing out of the hills, but as it comes toward Banks Peninsula is a bit of a barrier, and it divides the groundwater flow. So if you put all this together, what it means is that Christchurch's groundwater system is pretty much restricted to that area outlined in red. And the groundwater beneath Christchurch comes from two things. It comes from the river itself, from the Waimakariri River, which provides actually most of the water beneath the city. And it comes from rain that falls on the city, especially in the western part of the city. Now, this is a map view. I'm gonna move to a bit more of a three-dimensional view, a bit more of a cartoon, and zooming in on that sort of red outline area. So this is what you call a block diagram. You can see the map on the top of the block, but on the side, it's a vertical cross-section cut through the gravels to show you basically what's happening with the groundwater system in that third dimension. Now there's a few colors on this diagram and a few shades of blue. First of all, you'll notice on the right side of the diagram, there's sort of interfigured dark blue and light blue. The dark blue represents layers of finer sediments that aren't so gravelly. They're more sands and peats. So what's happened here is that over time, that coastal area, the eastern part of the city, has been near the coast, off and on as sea level has risen and fallen. And when it's near the coast, it tends not to be the same gravelly environment that you get farther up the plains. You have beaches and lagoons and swamps. And the deposits that get laid there are a variety of swampy peat deposits, dune sands, beach sands, and also gravelly channels, because the Waimakariri River sort of swings back and forth, and sometimes it does flow right through the city. So overall, those layers of finer material, they don't prevent the groundwater flowing through them. Those yellow arrows show where the groundwater is flowing, and the groundwater does actually flow right across those layers, but it does slow the flow down a bit. The other two shades of blue, the pale blue and the medium blue, they represent gravels. They represent groundwater within basically gravelly sediments. And the two colors represent those two sources of water that I talked about. The light blue represents water flowing out of or seeping out of the bank of the Waimakariri River. Now that water coming out of the river is really very clean. The water in the river is basically rainfall. It's basically rainwater that's fallen in the mountains and flowed down the plains. And the Waimakariri River doesn't actually have a lot of streams flowing into it once it gets down into the plains. It's basically alpine water. It has very low concentrations of any contaminants. It does have sediment in it. It does have some bacteria in it, but those get filtered out pretty quickly as that water seeps through those gravels. So when it ends up under the city, it really is very clean, and that is mostly what the city water supply is made of. Now on top of that, there's a layer of medium blue. That represents water that has come from rain that's fallen on the land surface and soaked through the soil. Now, because that river water is the dominant source and makes up most of the water, it dominates and it flows underneath, and that soil drainage water sits on top and forms a relatively thin layer of water on top of the cleaner river water. But it's that soil drainage water that is most likely to carry more contaminants, because it's percolated through the soil and it's picked up whatever the soil has to offer to dissolve into the water. So that's where you're likely to get any agricultural chemicals, nitrate and fertilizers, bacteria from grazing animals or septic tanks, any industrial chemicals from spills. That's where they're going to be. They're going to be in that shallower groundwater that comes from that soil drainage. Now, I said that the water basically seeps out of the Waimakariri River and flows underneath the city. And then that soil drainage water sits on top of it and also flows under the city. The other thing to think about with groundwater is all this water is fresh water. As it comes to the coast, it meets seawater. Fresh water is less dense than seawater, so it floats. So as this whole groundwater system flows toward the coast, it gets forced back upward by the density of the seawater. And because it's also working with these interfingered finer sediments, it doesn't flow as easily through them as it does a bit farther up the plains at the top edge of those sediments. So most of the flow actually comes back out again near the upper edge of that area of finer grained sediments. And when the groundwater flows out of the ground, it makes springs. This is Redwood Springs in Redwood. This is a place where if you go here, I don't know if you've ever been here before, it's really quite interesting. You can go stand on that wooden platform, you look down into the water, and you can watch the water bubbling out of the ground. It looks almost like the bubbling mud pools in Rotorua. It's quite interesting. But there are springs all over the city, and they do tend to be largely along that upper edge of that layer of finer sediments that marks the start of those sort of more coastal sediments. Now I mentioned the other thing that we like the groundwater for is our drinking water, and I just thought you might be interested where this water comes from. These are water supply wells. They're dotted all over the city. You may have seen them. You may have seen them and not even realize what they were. A little pumping station at the top, a little manhole in a park somewhere. But if you look in the manhole, you'll see a well. And that well is just like that straw we put in our glass. It's a metal pipe that goes down into the ground and sucks out water. And those wells, as I said, they're dotted all over the city. There's over 150 of these wells dotted across the city, and in 60 or 70 pumping stations. I'm not sure the exact number, I can't remember, but yeah, they're dotted all over the city. We've got these pipes going into the ground and sucking out water. That's where our water comes from. The wells are a variety of depths. Some of them are 20, 30 meters deep. Some of them are down toward 200 meters deep or more. And they are penetrating this interlayered, gravelly, sandy, silty sediments that underlie the city. Mostly, they are tapping into that river water. They're tapping into water coming out of the Waimakariri River and flowing back upward toward those sediments. Some of them are actually flowing artesian wells. In other words, you poke a hole in the ground and the water comes out of the ground out of its own accord, because at depth, that water is under more pressure than it's at the surface. So it actually gets forced upwards. A few of them, the shallower ones, will be screened closer to that medium blue layer, the land surface recharge. Those wells, if you look at the chemistry of them, it will be a little bit different. It won't be quite as clear as the river water, although in most of the city, the water is still very clear. That land surface recharge layer is quite thin, and to the west of the city, for the most part, there's not a lot going on that contributes contaminants to the groundwater. If you look at, on the far left of the slide, you'll see that bit of the cross section that comes away from the river. And you'll see that medium blue layer gets a lot thicker as you get away from the river, as you get more land up gradient of it contributing soil drainage water to the groundwater. And we do see that, the effect of that in our chemistry results from the samples we collect. Samples that we collect from wells that are closer to the river, or at least in the northern half of the city, look pretty much like river water. Very clean, very low concentrations of any dissolved salts or any other contaminants. But as you get farther south, to the southern part of the city, we do see higher concentrations of things like nitrate, chloride, other dissolved salts. It's in the southern part of the city that we see any signs of industrial contaminants, hydrocarbons, petroleum compounds. Again, we don't see very high concentrations at all, but we do see traces to the south where we see really nothing to the north. And in fact, if you were to sample the water in the streams, in the Avon and the Styx, the Heathcote, you'd see the same sort of thing. The Styx has water chemistry very much like the Waimakariri River. The Avon River has slightly higher nitrate concentrations. The Heathcote, farther to the south, has higher still nitrate concentrations. So, in terms of risks to Christchurch's drinking water, the main risks are in the western part of the city. The main risks come from development in the western part of the city and shallow wells in the western part of the city. Developments in that western part of the city, they're not going to affect most of the groundwater beneath the city. And in that respect, the city is really very lucky. It's got this source of clean river water coming upwards under most of the city. However, that can only provide so much water for the city, and as the city grows, more of the supply will have to move westward as well. So what we really need to be careful of as the city grows and develops is what happens in that western part of the city. If we have development, we have to make sure that wastewater systems are constructed properly. If we have any industries out there, well, we probably want to avoid heavy industries if we can, but we need to make sure that any chemical storage is robust, that they have systems in place to collect spills and to clean up any spills that happen. A lot of engineering can reduce the risks quite a lot, and yeah, a lot of good management and being a bit careful about what does go on out there. But that's really the main risk to the city. For the most part, that eastern part of Christchurch is really looking pretty good. Now, just before I finish, I did want to talk about the flows in some of these streams because they have been making the media lately, and there are talks of some of the streams in western Christchurch going dry when they haven't gone dry as long as anyone can remember. As I said, those streams are fed primarily by groundwater, and the flows in the streams are related to how high the water table is in the western part of the city. What this slide shows is two graphs. The top one shows the groundwater levels in a monitoring well that we monitor out near the airport. And we measure the water level in that well pretty much every day. We've got automatic recorders there that measure the water level every day. So that top graph shows the water table in depth in meters below the ground surface over the past 10 years. The far left of the graph is 2006. The vertical lines show every year. So each vertical line shows January 1st of the next year. You can see that the water levels go up and down. And the more you look at it, the more you see that it is pretty much an annual cycle. The water levels are highest in the winter, and they go down in the summer. The graph on the bottom shows rainfall. Rainfall measured at the Christchurch Airport, monthly rainfall. The average monthly rainfall in the city is about 50 millimeters per month. And you can't see as much of a seasonal cycle in the rainfall. You can get heavy rainfall at any time of year, really. But if you match the rainfall in the bottom to the water levels in the top, what you see is that the water levels come up when you have a wet winter. Take that first year, 2006. In January 2006, the water levels in that well, so the water table in the western part of Christchurch, was fairly low. Then, in the winter, that was the winter we had the big snowfall, if you remember that. It was quite a wet winter, and the water level rose quite a lot, fairly quickly over the course of that winter. And then over the summer, it dropped off again. There was quite a lot of rain in that January, or maybe December 2006, January 2007, and there was a little blip. The water level went up a little bit, but not a lot compared to how much rain there was in that month. Thing is, in the summer, the soils are dry, water is evaporating, so a lot of the rain that falls in the soil evaporates before it can soak through to the groundwater. It's really in the winter, when those evaporation rates are low, that there's a lot of excess groundwater to replenish the groundwater system and raise the water table. And you see that pattern all the way across until you get to, look at 2014 toward the right side. That top graph, look at the bottom graph first. 2014, there was a lot of rain in the autumn of 2014. Quite a lot of wet months, several months in a row with rainfall of more than 100 millimeters. And in response, the water tables went up quite a lot. Since that time, we really haven't had a lot of rain. We had a little bit of rain last winter, and there was a little bit of blip, a little bit of a rise in the water table, but there wasn't a lot of groundwater recharge. And you'll see right at the very right-hand side of the plot, of the rainfall plot, we did have quite a bit of rain in February, but it didn't really register in the groundwater table. Basically, the groundwater table is very low, and it is low primarily because of the rainfall, because we just haven't had that winter rain for 2 years. And even though we started off in 2014 with quite high groundwater levels, they've dropped off since then because we haven't had the recharge to keep the system going. Are the low flows a result of irrigation on the plains? Well, first of all, if you think about that first map that I showed, what happens on the Central Plains doesn't really affect Christchurch's groundwater system all that much. That groundwater is flowing to the south toward Lake Ellesmere. And second, when you look at this, it's really that winter rainfall that gives us the match to the water table. If there was no irrigation, if there was no groundwater being taken from the city for our water supply, would those groundwater levels be a bit higher? They probably would. Would the flows in the streams be a bit higher? They probably would. But overall, it is really the rainfall and that winter recharge that drives the water levels. And I think that's the end of it for me. Thank you.